All right, DE students, this lesson is 2.3.3, and we are looking at multiplexed signals and demultiplex signals. So this lesson, again, we're in two parts. We're going to start by talking about multiplexed, and then we're going to talk about demultiplex signals. So we're covering a lot of information in this particular lesson. So we are talking about the basic functions of multiplexers, which we also call MUX, the typical applications for a MUX, and then how we use a 4:1 MUX with small scale integration, or SSI, and then the different types of medium scale integration. And then also we then switch gears and do the demultiplexer, or DEMUX, and we're going to look at the same thing: typical application, the 1-4 design with SSI, and then the MSI for medium scale integration. And then we're going to look at how that actually integrates with the 7-segment display. So let's start by looking at multiplexers. We also call multiplexers MUX. So when you hear me talk about a MUX, I'm referring to a multiplexer. So what is a MUX? So a MUX is a digital switch that has multiple inputs and a single output destination. So the select lines determine which input is connected to the output. So it essentially acts as a switch, so to speak. If you look at the block diagram over here, you see that we have our inputs or sources, and we have one final output, and then we have our select lines over here. So we have a couple of different mainstream type of multiplexers. So the first is a 2-to-1, so we have one select line; 4-to-1, 2 select lines; 8-to-1, 3 select lines; and 16-to-1, 4 select lines. So those are the different types of MUXes or multiplexers that we can have to use in a circuit. So when do we use a multiplexer or a MUX? Well, that's when we have multiple sources. So this on this slide is an example. So let's say we have a surround sound system, and we want to be able to connect a MP3 player docking station. In most cases, this would probably be, these days, a Bluetooth connection from your cell phone, your laptop sound card, a digital satellite, so maybe a TV station, or, as it says down below, a digital cable TV. So not the best examples for modern times, but let's just go with it. So we have 4 different inputs, whatever they may be, and they are going into the selector, which is our MUX. So then, depending on the binary sequence, 0, 0, 0, 1, 1, 0, or 1, 1, that is what determines what's going to the surround sound. So if our selector is set to 0, 0, that means the MP3 is going to the surround sound. If it's set to 1, 1, the cable TV is going to our 1 output in this case. So this is a 4-to-1 MUX example. So this is what's happening inside of that multiplexer. So you'll notice that we have our 4 inputs, and then we have B and A. These are our selector channels, and then Y is our final output. So it's controlled by these AND gates and a final OR gate and some inverters. So what's happening then is, as we have B and A set to 0, it's giving us option 1. 0, 1 is tied to option 2. 1, 0 is option 3. And then 1, 1 would be D3, or option 4. That's controlled because when these are going through here, this is what's allowing this sequence of logic to come through to create that output. So all of this is happening inside the multiplexer to control whatever application is on this opposite end. So this is just the waveform that goes with a multiplexer. So basically, these are the sequences of waves for the input data. So D0 through D3, these are our input waveforms. So this is what's coming in to the MUX. And then the select line is functioning with these square waveforms. And then our output data is here. So if we were to look at the periods of these, we can notice that we have different high and low signals depending on where we are in our in the sequences. So this is just a graphical representation of what is happening. You do not need to measure sine waves for this assignment. You do not need to analyze them. This is, again, just a graphic representation of that internal function inside of the MUX. So medium scale integration for MUX is that 4-to-1. You saw an example of that already. So we have our 4 inputs, and then we have our select channel, and then we have an enable down here at the bottom. And then we have our final output and an inverted output as well. Same function for 8 to 1. It's just that we have more inputs, more select channels. We still have that enable. And then we have the output and the inverted output. And then 16 to 1, again, more select channels, still have the enable, still have our outputs. So now let's take a look at the De-Multiplexer, or the DEMUX. So a De-Multiplexer is a digital switch with a single input and multiple outputs. So this is where we have one thing coming in and we want it to go to multiple destinations. So the select lines determine which output the input is connected to. So the DEMUX types that we have, very similar to the MUX types, we have a 1 to 2 with 1 select line, a 1 to 4 with 2 select lines, the 1 to 8 with 3 select lines, and then the 1 to 16 with the 4 select lines. So over here you see the block diagram. So similar to the MUX, the difference is that we have one input and multiple outputs, and then our select lines in the center. So here's our application for a DEMUX. I apologize for the ancient looking clip art over here, but let's say our single source is a desktop computer and we need that desktop computer to go to a laser printer, a fax machine, a color inkjet printer, and a pen plotter. This actually would not be an uncommon setup inside of a traditional in-school classroom. So if you guys think about F305, that computer, that teacher computer at the front, it can print to the laser printer that's in the back. It is connected to actually the fax machine at the main office. We do have a fax machine in our school building. It's in the main office, in Miss Black's office. It is connected to a color printer in F310, so that faculty staff room across the hall. And it's also connected to our poster printer. So let's say that this is the teacher computer in F305 and I have all of these destinations. I need to be able to select the destination from my desktop computer. So that's where that DEMUX comes in. Now, this is a digital electronic way to control this. There's also networking applications that do something similar through the servers and networks within our school building. But let's say it was a DEMUX. That would mean that when it's set to 0, 0, I would be able to get to the black and white laser printer. If it was set to 1, 0, I would get to the inkjet printer, or 1, 1, I would get to the poster printer situation. So this is what's happening on the inside of the De-Multiplexer, which is the DEMUX. So again, this is kind of like the reverse of the multiplexer. We have the multiple outputs, one input, and we have the inverters controlling down here. So if we look at this truth table, this is what kind of process is to be able to determine what output we're going to. Excuse me. So again, this is just another graphical representation of what's happening. Our input data is here. Our select lines are here, and then we have our outputs and where they are going. So you can see if we look at different periods where our high and low signals are, we can kind of track what's happening inside of that multiplexer using the waveforms. Again, you're not going to have to do this in your assignment. This is just another graphical representation of what's happening inside the DEMUX. So this is our medium scale integration for DEMUX. So over here we have the 1 to 4. So we have our input, which is inverted down here. And then we have our select channels and our 4 outputs. Now you'll notice compared to the multiplexer, this was an enable, not an input. This down here is the input on the DEMUX. Okay, so just make sure that you note that most MSI DEMUXs, like the 3 that are on this slide, have outputs that are inverted, and that's done because it requires fewer logic gates to actually implement them if we have those inverses there instead. So that's why we have the outputs as inverted over here, that little notation. So that is typical when we see a DEMUX, is that the outputs are actually inverted inside of that. So this slide is basically just to inform you that seeing is not always believing, and that our labs are filled with electronic signs that display time, temperature, scoreboards, all that stuff. However, what we see is not always what's actually happening. For most of these displays, the individual display segments are actually cycled through so that only one display is on at a given time. And the cycle speed is so fast that the human eye perceives that all of the segments are on. So basically these are having like a shutter speed on a camera that's so fast the human eye doesn't detect it. But we perceive it as all of it. So as an example, like if we were looking at this number 8, it might be that segment G is flashing really quickly and then it's rotating through the rest of the segments, but we, with our human eye, see it as a number 8 the entire time. So that is just a heads up that with these 7-segment displays, we do have like a blinking situation that can occur, and that's controlled internally within the circuit. So that is how we tie in multiplexers and demultiplexers to these 7-segment displays. So the circuit on the right uses 4 7-segment displays to display the word chow. So in this circuit, all the displays are continuously illuminated, and each one is displaying one letter in the word. While this method works, it's actually a really inefficient use of power. To illuminate a simple message like chow, we need to have 18 segments continuously on, so we're using a lot of power. So would there be an alternative way that we could create this message without drawing so much power? If you said yes, you're correct. When we go and take a multiplexer and put it into this situation, we can actually control one 7-segment display at a time. So in this circuit, the display segments are multiplexed, meaning that we only have one on at a time. So to display the entire word, the displays have to be demultiplexed using the 1 to 4 DEMUX. So in this example, the select lines that control the DEMUX are connected to the 2 switches, and you have to toggle through 00, 01, 10, 11 to see the entire message. So basically it starts with the C, then you would have the I, the A, and the O, and it would basically be like boop, 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 and that's how you would get your message across. It uses way less power because we only have one segment display on at a time. So this is what that complete design would look like. We would actually have it set up with a ripple counter. So this is exactly what you did in the game where you had to do the random number generator and create that die where it output a number of 1 through 6. So the ripple counter, which is exactly the same as what we use there, actually creates a counter situation where it will cycle through the DEMUX to create this display. We are not getting to ripple counters in this situation yet. We're going to do it manually, but this is big picture of how we would control this circuit.